Hello, hello. Can you hear me? Do we need this microphone really? Is it better with microphone? Should I keep it? Yeah, no, use the. Okay. We're gonna keep it away from us right here. All right. Um, Welcome. This is Advanced Structures. And first of all, everybody here has had structures 1 and 2 or intermediate. Is there anybody you have not?
Yeah, I have. Sorry, I'm so she's making it. I'm just quick.
Okay. But you did have structures intermediate. Okay, good. Um, that's the prerequisite. And those are so you know the room, the hours. So we have kind of combined the 2 sessions per week. So we're going to meet once a week in 3 hours. We're going to have like a 10-minute break in between. But once a week, which is a little bit complicated in terms of your deliverables, which means we come to the class every week, and then we should have all of the homeworks, projects, due phases, all of them followed up next week. So if you miss a week, which means that it's really hard to catch up. So that's the only challenge, but you'll have a full week to work on things. I think it's more manageable in terms of the materials you're gonna go through. We have a TA, Lauren. She will be working with us on the homeworks and test preps. And our course coordinator, Professor Rageb. And the other section is twice a week with Professor Fowler. Let's see if we can go through some materials. Okay, a little bit about me. My name is Omid Olian. You can call me Omid. You don't have to call me Professor Olian or anything like that. I am a structural engineer, researcher, and computational designer. My background is in structures and architecture, and my PhD is in architectural technology with a focus on computational design. Here are some of the engineering works related to our coursework that I worked on. We're going to use these as some reference projects throughout the course if you get a chance. This is an extension for a concert hall in Czech Republic by Stephen Hall. And we worked on a workflow to optimize the structure based on constructability issues of grid shell pipe sections. This is a schematic design level for Claremont McKenna College by big architects. This is relevant in terms of the type of larger scale truss works that work as both lateral and gravitational workflow. And we worked on designing this based on accessibility and structural aspects. This is an example of dome structure. This is a renovation project and studying the performance of dome. This is a Park Synagogue in Cleveland, Ohio. This is challenges regarding application of wind loads on dome structures and finding retrofitting measures. This is a good example of how we use different materials for basically retrofitting existing buildings. This is buildings by NYCHA for affordable housing. The issue was the roof of these buildings is very old and it's leaking. So there's a lot of expensive measures that needs to happen for the roof structure. And instead, this was a proposal to use mass timber to build a rooftop, basically a community garden as well. And the idea was how to use lightweight materials in a way that the location of columns is optimized so we don't need any retrofitting for the foundations. That was why we went to mass timber. Also, some of the design build projects and research work that I do, this is what I designed for the entrance of botanical gardens. Do people know Matai Botanical Gardens? It's a cool place for hikes and has a good conservatory. This was done as part of my research in my PhD, and we got a grant to design and build this piece. It was sitting there for 2 years. This was a more recent consulting work that I was doing. Again, this was built at Matai Botanical Gardens. This is robotic fabrication of lightweight timber structures. This relates to the ideas that we're going to use in this term. It's interesting to think about reusing materials. This is small pieces of wood coming together so they can be recycled wood, reclaimed wood, and using robotic fabrication to take care of the complexity of assembly process. This was another research design build project that was done at the University of Michigan. And the idea was to replace the connections in heavy timber joinery. Instead, we used 3 forks. And this was the idea of going to these timber yards, finding these scrap material, bringing them, scanning them, figuring out a workflow that we can design them as connection pieces. I also did some projects at LTU and engaged in design build courses here. This was retrofitting measures for this arch. I don't know, have people seen this arch? It was sitting on your campus, yeah. So the idea was to analyze it to figure out if we can put some retrofitting measures in case we want to use it long term. This was how analysis informed figuring out those measures in terms of bracing, infills, and things like that. Also, I was teaching the design build courses for this summer. These are sculptural pieces you see around the campus. This is the shrink wrap. The structure was rebar system, and the cladding is shrink wrap, basically creating that funnel shape. This was all designed and built by the students throughout summer. Hopefully you get a chance to do these. This is a lot of interesting things that your fabrication, design, structural analysis, structural aspects all come together and you figure them out firsthand. So these are quite interesting projects. This was the other one, which is box beam with a wood grid shell. That was all designed by this group of 25 students. So there were 75 students, 3 groups, 25 each. They had 5,000. They were designing this. This is another one which is at the entrance. This is interesting in terms of the lightweight wood framing, and then how they figured out the complex geometry using just linear elements. Okay. Hopefully we get a chance to talk about this type of projects as we work through the coursework. But in terms of the syllabus, first of all, do everybody have access to Canvas? Is there anybody who doesn't have access? Yes, you're not in there, but you will be added to the course and you should be fine. But let me know. We're going to be in contact for the next 2 days. So you should have access to syllabus and you should already have gone through this. I'd like to review this together to make sure that we cover all the materials. Also, during this class, at any point you have questions, just ask questions right away. You don't have to wait. I don't mind interruption regarding the coursework or any other relatable question. Okay. Let's see if we can share this. Right, it's good. I'm going to talk about Canvas files. We have some folders in Canvas that we share the information about the course and materials there. Course description, please read through these and let me know if you have any questions. We got the lectures. So this is lecture based, of course. Every session we have 2 lectures. And I'm recording these lectures right now. Hopefully it's working. I'm not really sure. Let's see. So we are recording these lectures, so it's going to be available for you. I'll post these after the class I post this after the class through YouTube link. Is that good? Okay. So you'll have access to recordings. You'll also have access to lecture notes. This is part of the files in Canvas that you get access to all of these notes. We have lab quizzes. Lab quizzes are basically projects that you'll do. There are 3 of them, and there are pairs of 2 students. You pair up with another student. And these are extended projects, different types. You have 3 of them. They have different phases of submission, and you should submit these based on each phase on the due date. All of this information will be shared. Right now, quiz 1 is shared. Did everybody got the announcement about quiz 1? You see nods. Some people haven't seen it yet. Oh, it's okay. So you should receive an announcement about quiz 1. And it has 3 phases, and each phase has deliverables. The first deliverable, we're gonna look at the schedule. It's coming up, I guess. I'm not sure. We'll check. Exams, we'll have 3 tests and 1 final exam. So, and those are a big chunk of your grade. And it's important, you can't really wait until the last minute to study for them. So all the homeworks relate to those exams. So you better follow up with the homeworks, submit them on time, and to be prepared for them. Otherwise, it's going to be challenging to do that just one night. The TA will help you with homeworks and also the test prep. So if you have any questions, you can reach out to her. And also to me, if you have any questions during the class, you can bring up your questions. We can discuss them. There's a course software that we'll discuss later. We have free access to that. Grading policy. Okay, so here is your breakdown of your grade. Homeworks. So we have homework submissions every week, and that's 10%. But highly recommend keep the due dates, review the homeworks, submit them on time. That's how you will be prepared for the test. I will share the homework answers later past due date. So you should really keep up the due dates, but the homework answers will help you to understand that. But if you have any questions, talk to your TA or bring your questions here. The test, you have 3 tests and then final exam. You see 60%. You have to really do a good job on that to get a passing grade. You have quizzes. There are 3 projects, team of 2, and that's 20%. And each of them have different phases. So weekly, as maybe 1/3 of the class will be just going through your submissions every week or on the due dates. Also, attendance is mandatory. Do not miss a class. This is 10%. And also, you have to be present to ask your questions, understand the lecture content. So that's part of the grade 2. And we'll take attendance at the end of the class. Any questions about the grading? Once we talk about the projects, you'll know the nature of those projects, but everything will be shared the week before. Yeah. What's that? No, it's going to be a cumulative of all the tests. Yes, and each test is just that chunk that you pass. For example, first 4 lectures is test 1. Any other question? Okay, this is the academic calendar. Make sure that you check your last day of dropping is what? September 2nd, where you can get your refund. And then the last day is Oh no, last day is September 6th, but you get refunded. And the last day of drop off, November 22nd? Yeah. Make sure you check the calendar. There's a link in your syllabus. Also, let's take a look at the schedule. Okay, here's the schedule. 16 weeks, dates that we meet, the lectures we cover. The lectures will be available a week before, and you're supposed to review all the lectures before coming to class and bring your questions. So you got to go through the lectures, come here prepared, then we're going to discuss the lectures. And the first half and one last third of the class will go over your projects. And lab quiz 1 is issued, and next week is Labor Day, so we don't have a class. And we're gonna come back on September 9th. So phase 1 of lab quiz 1 is due. Is there any questions about the schedule? Okay, take a look at it. Let me know if you have any questions. Everything should be self-explanatory, but let me know. And lab quiz 1. Okay, so this is lab quiz 1, for example. This is shared. You should have access to this. Please check first thing that you have access to this. The first assignment is to build your team. This is a team of 2. And you should choose your project from list of projects, which is given at the end of this project description. These are series of projects that this is a case study project, basically. You go through the project, you understand the project, you explain, you first do a good research, find as much material as you need in terms of the structure, integration, architectural aspect, to answer series of questions here. So this is the phase 1, which is due on September 9th. So you go through all of these questions. First of all, you should choose your project. And because you have 18 students, so 9 teams, this is first come, first serve, no duplicate in projects. And for that, in the description of in the announcements, I guess I sent you, there's a Google Sheet that you, okay. Let me share this. So here is the announcement. Since it's first come, first serve, the first thing after the class, go through those projects. And there's a Google Sheet here. You need to find your teammate, put the name. Oh, you're already done. Look at this. Pretty good. See, that's getting filled up pretty fast. So find your teammate, you see, find a cool team name, and so you should find a teammate. Forgot your name. What was your name all the way back? What is your name? Oh, you're already a team. All right. Just wanted to make sure you have a teammate. Okay, good. So fill this on. I guess everybody already have, or you're close. Perfect. So you need to do the first phase, do a further research into your material, find other links. When you come into class next week, next session, I want to see your research, the links you're using, and answer all these questions. And if your research is not enough, I'll ask you to do further research to accommodate all those questions. Okay. Is there any questions about the quiz? Non-structural. Okay. Yeah, so we have 18 people, so there's even up. Yeah. Don't we? I thought so. We are even. Okay. So the decision with the other section was we can't have 3 members, so there will be a 1-member team with reduced load, but I don't like that. It's hard to manage. It's not gonna work well. So you can have 3 members. I know you're the person. Okay. Who else doesn't have a teammate right now? Who doesn't have a okay, you just join one of the teams. But I expect you better representation, better research, of course, right? So okay. Yeah. Yeah. So it's gonna be the best project. All right. I guess we covered everything. Homeworks. Okay. So the first homework is due accession. Do we have access to the first homework? Do people know the first homework is issued? Okay, so homeworks are in your grade book. The first homework is all right. Here's the first homework. And this one is a PDF upload. The rest of your homeworks is online through your gradebook. You just enter calculation numbers. But this one is 2 readings. There are links, but there are also the PDFs if you don't have access to them for any reason. But you read the readings, answer questions, and there are some simple span calculations. Write these in the PDF or Word and upload them. Your TA will go over them, grade them, and will answer any questions. Any questions about the homeworks? Do everybody know? No, just this one is. The rest of them is online thing. You just enter numbers. Yeah. There should be one.
There's one that's been fulfilled the 16th of December, and there's one that doesn't have a due date.
Let's see.
Canvas is weird.
Okay. I'm talking about this one. So Word PDF upload. Is that clear? Awesome. Okay. But let me know if you had any issues with the homework, let me know early on so you don't have to do that. These are due every week, basically. Okay, now that we are here, I can show you the files. So for everybody should have access to these folders. Do people have access to these folders? Good, 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 good. Is there anybody except you who doesn't have access? All right. So here are the folders. Digital lectures. This is where every week I upload your lectures, so you read them before coming to class. There is assignments homework. I'm gonna upload the assignments too. Oh, this is older. This is assignment 2024. I'm gonna upload the homeworks here too for your reference. I will also upload the answer to homeworks later when the due date is passed. There are quizzes. I upload quizzes here for reference, but also you get links to your announcements every time it's due. This is important. These are past quizzes. So these are submissions from past student projects. Go through them to familiarize yourself with the formats, content, representation. So this is for you to get some ideas what is required in the end and kind of enhance your submissions. Syllabus and schedule, of course, are here. And then past exams are also here for your reference. And we're going to talk about them later, but you have access to all of these so you can review them and ask questions if you have any questions. Any questions about the content of Canvas or working with Canvas? I expect all of you are good with Canvas, better than me. Okay, good. But let me know. And also your TA about this. I'm gonna send an introduction announcement later today to have, so you have your TA's email. But for right now, here is Lauren Moon, L Moon at LTU. Okay. Did you cover everything? I think so. Right. Good. Any questions before we get to the course? External display is disconnected. All right. Um, all right. So the first two lectures in the course are basically an overview of construction systems. This is bigger picture on the structural systems, materials, based on the spans they work, the type of construction. This is an overview of everything. And then we're going to dive deep into every type and get into analysis, analytical aspects, and all the fun stuff. This is good to do this overview as you start your first project. So to understand the structural systems, these are the topics you're going to do research on and expand in your quiz. There are two textbooks that you will be using, mostly this one. Structures by Daniel Schroeder. I highly recommend you guys get this. This is a good architectural engineering type course, a textbook. It does have both calculations, but in a very intuitive way. So it's very easy to read. It has a nice organization. It has very good visual and also textual explanations. I highly recommend this. A lot of the content of these presentations, which Professor Fauro have put together, is based on this course book, and then also, of course, expands beyond it. And there's this one, which is more of a engineering aspect of it, but for architecture students, but there are some topics in this book that I like a lot when it gets to load pass and system analysis that I haven't seen in really other book. So these two, this one is Aesthetics and Strengths of Materials by Barry Onwoy, for those who like more technical aspects. You probably studied part of this in your structure 1 and 2. Okay. We're gonna follow through the same presentations at the other section, and we're gonna engage with some extra material as needed. Feel free to ask questions during the class as we move forward. So the first aspect of this is structural categories based on material. What are the main materials in structural systems? What are the main materials? Damn. Yeah, of course. These are the main materials, and we're going to talk about these 3 structural materials in the context of how these materials translate to structural systems. So we have different materials, but they can be applied to many different similar and very different structural systems. And the codes basically restrict the use of certain materials for certain conditions. And what's the main reason for that? Fire resistance. So IBC, International Building Code, this is from 2006. The new version came out this year, 2024. Have 5 categories that the structural systems are. So based on what you design, it's restricted, what kind of material you can use, what kind of height, how high you can go, whether it's concrete or wood. And also what type of occupancy is it? Is it residential? Is it commercial? Is it industrial? Those have different categories which have different requirements for fire safety and different requirements for the type of interior material you use. There are many different categorization of structures. This is the main one, building categories. So there are different categories based on importance, which is mostly based on occupancy. There are categories based on seismicity or wind, which again gets into safety of the structure. But this is one of the overall categorization. Type 1, high-rise buildings, buildings of higher importance, hospitals, larger scale commercials. Type 2, mid-rise buildings, schools, hotels, but again, different type of materials, steel and concrete, ordinary construction, heavy timber, older heavy timber structures like churches or barns, wood framed. The wood framed is more a modern stick frame, stud wall, joisted floor systems. These are very simplified rules of thumb for selecting structural systems, but of course it gets more complicated, but this is useful if you want to just get an idea what type of construction, what type of a structural system you can use. This is a useful table based on, so the first material is studying is wood. This is a very useful table, again, rules of thumb. For the type of structural systems on lumber, plywood, planks, SIPs. What are SIPs? SIP panel. What is it? Structurally insulated panel. These are the ones which have plywood or OSB on 2 sides with infill insulation. Joists, beams, girders, engineered lumber. What is engineered lumber? Come on. Yeah, that's one. GLT, glue laminated timber, DLT, dowel laminated. NLT, nail laminated timber, CLT, cross laminated timber, but even I-joists that have dimension lumber and OSB in the center. It basically means you use dimensional lumber to create different types of structural wooden members. Truss joists, truss longest span, folded plates. Folded plates is both can be cross-laminated folded plate with finger joints or plywood folded plate systems. These are specialty systems. Timber framing system. This is kind of an overall advantages and disadvantages of wood. Um, Basically, wood is one of the oldest materials that have been used, and it's lightweight, but it's combustible, which means have fire hazard. Also, it's lightweight. It means that like more lightweight structural system, lightweight structure, smaller foundations. Um, Working with wood is more forgiving. You can have a design for design build projects. You can play with the geometry. There's always like undulations on site that you didn't account for. You can kind of massage the geometry, push them, cut them, nail them. So, but if you have a steel construction, you have to be accurate and it's harder to work with that. Or concrete, when you pour it, there's formwork that you need to work on, has its own complications. Timber in long span construction. Um, so again, all these different materials can be used in structural systems, different types of structural systems. You can have domes made of lumber. You can have truss systems made of lumber, steel, concrete, even concrete, or different types of structural systems, which is discrete system or it's a continuous system like um, shells, freeform geometries, um, beam and column, or more complex freeform structures. So the most well-known type of construction system with dimension lumber, what is it? Most of the modern wooden buildings. It's called platform construction, and that's the stud wall. Walls are stud walls covered with plywood and joisted floors, right? Um, that's a kind of a historical lightweight residential construction system. Here are some of the advantages. Building type, single family residential, multifamily. They have the stud walls are load-bearing walls. They also take lateral forces through the plywood, which is called the racking action. And yeah. Oh, the second one down lower here, we have a stress scheme panels. A stress scheme panels is imagine a stud wall horizontally. So you have a framing and then there is a plywood or OSB on top and bottom. Read through these, they're useful information about these systems. Box beam and engineered lumber framing. Again, box beam, you have a framing inside and plywood on two sides, which takes the shear basically. The dimension lumber is the structure and shear is taken by the plywood skin. Engineered lumber framing. On the right, you can see blue laminated timber, which is basically dimension lumber, adhesives as the connection, and it's heat treated, and they all work in the same manner. So basically, you create bigger cross section from the trees that are smaller. You have dimension lumber, you can have multi-feet deep glue laminated beam. Heavy timber framing. Heavy timber framing is more historical application of wood in its original form, right? So we cut the trees, we chop it up, we create beams and posts, and then it's kind of a craft actually to create these connections. Usually comes with um, uh, knee braces, and it needs to be detailed well, and it needs to be treated well from the moisture content. Otherwise, it will cause a lot of problems. It will have movements. As you know, wood, as it absorbs humidity, it expands and contracts and cause cracking. So more historical way of building, um, you can see that these buildings are um, kind of bendy a little bit because of the changes in moisture content. They're safe, but visually they change. It's kind of beautiful. The connections are simple. They are bolted, nailed. Lightweight framing wood trusses. These are prefab truss systems that again used in residential and also smaller commercial systems. Um, they are dimension lumber, and for connections, there are metal pieces. They're built, and the fabricators, production companies provide information about the span's capacity and construction details. Also, open web joists with wood and steel, the same process, the same system. Okay, any questions about wood and wood structures? Okay. Okay. The second material is concrete. Can someone tell me what is concrete? What is this material that we use? How is it? What is it made up of? Water. The important one, what is the glue? Uh-huh. So what concrete is a composite. It's a man-made composite. We have aggregate, we have sand, we have water, and then we have cement. Cement goes through process hydration, called hydration, and it kind of bonds these, so it creates a matrix, all these pieces are together. What is concrete good at? Tension or compression? Compression. What happens when concrete is in tension? Cracks. What do we do to reduce and control the cracking in concrete? Reinforcement. Exactly. So we have a material which is very strong in compression. It's like a man-made stone, right? But it easily cracks. And what we usually use concrete in is this post and beam systems, right? The beams are in bending. Bending means the lower part of the beam is going to tension and upper part goes into compression. The compression part is fine, but the tension part is weak. And as soon as you get tension in concrete, if it's not reinforced, the cracks appear and they propagate. So when we put tensile reinforcement in concrete beams, what we're doing is we're actually expecting the micro cracking. If there is load here, we have tension happening here and compression happening here. This is fine. Here we have cracks happening. We put the reinforcement, there we have tension. And once the beam cracks, then the tensile reinforcement here activates and it takes the tension. So this part is not actually working. What it does is it transfers this tension through friction that keeps the reinforcement in place, lower side. So what it means is that we need to know where in the geometry of our structure tension happens. So if we have simple beam like this, it's easy, right? We know which part is in tension, which part is in compression, and we put it there. But what happens when we have continuous beam? Ta-da. All right. from structures one, you know that the bending diagram is, first of all, you can think about deformation, right? It forms this way, kind of exaggerated, right? Bending, positive bending, negative bending. All right. Where should I put the reinforcement? Here. Where should I put it? Lower or upper? Lower. Exactly. Bending happens, tension happens here. I put the reinforcement here. Here. Where am I putting it? Why? Tension, exactly. This wants to bend it like this, so we have tension here. Wants to pull it apart, so I put my reinforcement here, and then again here. So this is interesting, right? So we are designing material, composite, and the add reinforcement where needed. This is simple beam. This idea can be applied to a freeform concrete shell. Then based on location of your supports, where it is, then you figure out where the reinforcement goes, right? The mesh goes on the lower side, or the mesh goes on the upper side. The same idea expands in 2D and in 3D. Great job. You guys are good. This is material characteristics. These are information about the how many days does it take for concrete to cure? What does it mean? What does it mean that it takes 28 to cure? Reaches its full strength. That's what is the full strength? Is that process of hydration that creates that bonding in the matrix takes 28 days. But like 70 days, 7 days, how much it gives? I think 50%, let's say. So it has 50% of this maximum compression capacity, and that's called F prime C. This is the compression capacity of concrete, and it depends on how much cement it has, what kind of aggregate it has, but mostly what type of cement it has. And as time goes by, this goes up to F prime C. That's like 7 days, 14 days, 28 days. It kind of reaches its capacity. This means that you have to plan that poured concrete weight that much to so we can apply the like you pour your, let's say your floors, you wait until you have that capacity to actually take out the scaffolding, and before it gets loaded or construction work is gone up. So it needs to be at least 75% or full 28 days. There are fast curing concretes for different projects and also different capacities of concrete, which is gained by admixtures, the chemicals you add that extremely can increase that. But for normal concretes, you have formulas for admixtures and the duration for curation, and it's what's applied. The elastic modulus. What is elastic modulus? This is something, the first thing you should know in structures. What is it? Okay, there are three. Okay, that's good because it has relation to that, but that's not what it is. Yeah, that it has relation with ductility. But what we know it as is if you get a cylinder of concrete, take it to the lab, put it in hydraulic jack and measure the deformations at the force that it applies. If it's force, this is deformation, it has something like that for concrete, for example. And it has some elastic phase, and this line, the slope of this line is E, which means how much we put force, how much we get deformation. So it is a measure of stiffness of that material. And that in concrete, for example, steel, the diagram if you draw for steel is like this. When you said about ductility, you're right for steel because it's a ductile material. This part is linear, this is E, but it takes energy until it suddenly fails, right? This, when you talked about ductility, is an area under this diagram, how much energy it absorbs before it fails. But when we talk about elastic modulus, it's the slope of elastic phase, which means if I stop loading here, take the load out, this jumps back up to its location. And for steel, they have these things, straps that we pull. For concrete, we compress it. For steel, we use tensile test. If I release it, it goes back. But if I pass this phase, if I release it, it doesn't go all the way back. It has plastic deformations. So in elastic phase, this is where we designed it, which means it goes back when I release the force. If I take the load, it goes back. Or for concrete, it goes back. For concrete, it's very small. But the slope of this is elastic modulus. So elastic modulus is a measure of how stiff a material is. And this in concrete relates to its F prime C, its capacity. In steel, it's not like this, but in concrete, there's a good measure of that. And E comes from a formula that I don't remember. There's something like, let's say, 5,000 or square root of F prime C. You see? So the type of concrete has different elastic modulus. But if you have certain type of steel, you have A36 or A50, which depends on the carbon in the steel, and it has certain E. The type of material has the same E, but they have different capacity. For steel, it's Fy. But in concrete, its stiffness has relation to its capacity. Okay. Reinforcing types, we talked about this. Slabs. So we talked about this in the slabs. We have welded mesh wires instead of in beams. It's rebar, and it slabs is that. Just 2D version of that. Okay, this is what we talked about. We put the reinforcement where it's needed. Concrete is not combustible, so it's fire resistant, of course. So we can use it in higher fire hazards. It's insulative too. And the way we work with concrete is there's a form where it can be poured, or there's cast in place, or they're prefabricated in a production company. They cast them in specific modules, and then it's transferred into site and then assembled on site. So whether cast in place or prefabricated, based on the complexity that we create for the formwork, we can create different geometries, so different systems. And if the project is big enough that it can create repetition, that prefabrication actually pays off, and the speed of delivery pays off. So whether it's a sculptural aspects in architecture that you use concrete for complex formwork, or the efficiency of prefabrication and repetition of design, it's a designer decision that how it plays, how it's scheduled, how it makes sense financially and economically. But the flexibility exists in the material that can provide both actions. Okay. Any questions about concrete? Okay, we are into steel. This is a fun table with the spans and kind of rules of thumb for type of construction and type of concrete systems. Let's see. You can use that as kind of a reference, as rules of thumb. But as I said, it depends on the type of loading. It depends on the system, how it's performing. So these are not accurate. This is just rules of thumb, but very useful for concept design and schematic, even schematic design. Cast in place systems. We talked about this for cast in place systems. We have formwork and we make concrete as mixtures. We pour them in the shapes we want, whether beam, columns, slabs, shells, and it cures. And we already have our rebars inside the formwork, and it cures, and the structure is load bearing. Flat slabs with drop panels. This is one of the common framing systems in concrete. We have flat slabs on top of columns. And as they're poured together, they fuse together, so they operate as one system. So they take bending, they have fixed joints. The problem with flat panel systems is that when you have flat panel on top of a very small column, there's something that one type of failure in the system. What is the sudden way of failing when you have a thin plate on top of a column? Punching shear, which means that the column completely goes through the panel, through the flat plate. So in order to do this, and this failure is type of a shear failure, right? It cuts through the panel. And this is the shear here that the column goes through this. So if I increase this depth, I can increase this length of this crack. And because of that, it's not gonna fall through, right? So we have flat plates with drop panels. These are called drop panels. That's a simple way to increase the punching shear capacity in flat plates. One-way slab on beam is basically a slabs that's sitting on top of columns. And this can be prefabricated, so the connections are not joined. So we have columns and then detail it as the prefab beam sits on top of it, right? Waffle slab. So imagine if you have a slab and these are columns in four corners. If I want to increase the load bearing capacity of this, I can add beams in the center, right? If I refine this grid, I have this network of beams on the lower side of the flat plate. That's called waffle slab. And waffle slabs are useful to span way further on. But the issue with that, what is the issue with waffle slab? Are they economically, why not? A lot of formwork. You are optimizing the system by creating a network, so you can span way longer. But there's a lot of formwork, and this is fiberglass formwork, foam core formwork, and that's although it's reusable, but it's very expensive, and because of scheduling, you have to have multiple of them for multiple floors. So it doesn't make sense for smaller projects, but again, if you have programming requirement for architectural aspects of the project, you want to have a very high open space, a very long open space. This is one of your choices, and you want to do concrete. What is the other issue with concrete in general? So actually, depending on what kind of system you're talking about, it's one of the good ways that you can integrate it with mass timber now. They do podiums, multiple, like 3 floors, and then do mass timber. But it can have issues with integration with mechanical systems, depending on what type of a structural system you use. And it's hard to, for example, pass through mechanical systems through the ceiling as part of our conversation when we talk about system integration. But is it environmentally good material to use? Why not?
The deconstruction of it in general sort of releases a lot of toxins into the air, and not to mention people who work with it have a lot of impact in their like, more likely to get like lung cancer.
Yeah.
Because they're cementous stuff.
Absolutely. Absolutely. So first of all, this production causes a lot of toxin. And that's perfect. Second of all, an important aspect, the demolition. When we demolish a concrete building, it all goes to waste. Now we're finding they're research into, okay, how can we reuse them as aggregate? But again, there are issues if there's metal in them, it's difficult to. There are some research that they're saying, okay, if you have a lot of slabs that comes out of these demolitions, how can we chunk these slabs in a way that then we can reuse pieces of the slab in form of masonry structure? But again, still in a phase of not a scalable research. More important than that is that this material has significant amount of energy embodied in it. Uh-huh.
It's wild. It feels like if you're doing a concrete building,
Uh-huh.
it's full of steel rebar anyway, so you might as well just do a steel building.
Yeah, that's a good point. The issue with concrete, or not the issue, the thing with concrete is it's cheap and it's accessible. Yeah, I hate it, but but that's the case. And because historically it came in as this structural material that is cheap and that can be shaped into different forms with different formworks. So it was flexible, it was accessible around anywhere in the globe. So you can access concrete, you can build your own concrete admixtures, you can put them together, put formwork, pour it in, there's a structure, and it's way cheaper. You don't need significant infrastructure for that. You can actually import your cementitious material and all that. But significant amount of energy goes into production. Production of cement causes a lot of carbon emissions. So, and again, you can't just use concrete as is. You need rebar, as you said. Rebar, metal, steel has significant environmental footprint. So there is something called embodied carbon, which means the amount of carbon emission that the material from the production all the way to demolition, if you do a full life cycle, contributes to the air. So this is released in the air and causes global warming. Concrete is terrible. So then we need to think about ways. So at any point of this, there are a lot of interesting architectural research on, at any point of this, if we can reduce that footprint while keeping it still cheap, because we can't just ban concrete because of, accessibility. So, and it's not going to go away, that I hope goes away, but it doesn't, is, okay, how can we make it better? So there are a couple of ways. There's some research on admixtures. How can we reduce the cementitious material, which is the most carbon emitting part, with fly ash or some different types of side products that we can use that doesn't have that much carbon footprint. The other aspect is, okay, if production is that much, how can we build less concrete material, less buildings? So then, okay, how can we integrate it with different systems? Or then okay, if we have to build with concrete, how can we optimize it? Then there's structural optimization and that, and then we reduce the material use. One step further is, okay, if we have to build it and we optimize it, what happens at demolition? Design for disassembly. Use prefab systems that can be disassembled and reused. So there are some research in that. So as you see, there are a lot of opportunities for still working with material, but consciously. How much calculate your carbon footprint, compare it with the steel or wood, compare it with hybrid systems, or concrete and then a podium of concrete and then mass timber. These are the ways you think about the material in a smart way. So you just not say concrete is bad and it's banned, because developing countries need it, a lot of places need it. But how can we do better? How can we make it less harmful to environment, right? Yeah. it's an interesting research area, and if somebody's interested, there's so many opportunities in this and definitely needed. Right now, there are thinking about one aspect of reducing the harm in concrete is okay, how can we get rid of the wasteful formwork? So 3D printing comes in, right? 3D printing concrete systems that actually are high performance. We print as much as we need, and we use less harmful materials in it. All right. Any questions, comments, concerns? Okay. This is an interesting application of waffle slab. Um, you see, it's the cardboard waffle structure is a good example of this, and this relates to the idea of transfer systems. If you have a stacking system at that building, and if this column is sitting in the middle of the flat plate, that's really bad design because punching shear, significant bending in those points, lack of redundancy. This is where the type of system, interlocking systems, waffle systems, and waffle slabs can come in handy as they distribute the load through the network of beams inside the system. Hand joist is basically ribbed concrete floors. Again, you have formwork, and then it creates ribs, which are basically beams, concrete beams, under cast in place with the concrete. This is a good chart to see the system type and number of stories. Again, rule of thumb. Okay. Flat slab, 1x2 way. We talked about this. A little bit more information. Flat slabs. This is a good example how playing with the flat slab in elevations. So the architectural form is basically replying to some sort of structural logic. And the back and forth and relative movement of these plates create the geometry of the zigzag shape of the tower, meaningful structurally. And it's very common application of flat plates merged with shear wall, concrete shear walls, and peripheral columnar systems. Waffle slab and precast slab, we talked about this. Precast channel and single T's. Again, in terms of precast construction with concrete, this has a long history and a lot of optimized systems. Where do you see precast channels and single and double T's in parking garages? It has nice detailing, right? The columns sit on top of it. It's most common in that, but also they use them in short span bridges. There are post-tensioned T-beams that are used double T's that stabilize better, because single T's, you need to stabilize them. But when you post-tension them, you basically put concrete in compression. So by creating that intentional compression in it, as it goes into tension, part of that embedded tension compression takes care of the tension. So you increase the load-bearing capacity and also creep in concrete. Creep is when the concrete form deforms under sustained load. So this is very important to understand as part of as a bigger picture of working with materials in structures. Our main three construction materials: concrete, steel, and wood. Tell me which one is a homogeneous material? Huh? Steel. What does homogeneous mean? It's all the same at any point in the material, right? But in more technical term, homogeneous means at any point in the material properties like E not Y is the same. And because the nature of that material, the crystalline nature of the steel, right? Is concrete homogeneous? Why not? Yeah, it is basically a composite. So you have aggregate, you have a matrix of cementitious material, and then you have your reinforcements. It's composite action between multiple types of materials, which E, E1, E2, E3, at any point, we have different materials. So how do we design it? We have E for concrete, we have E for steel, we design based on that, right? So we share the action. Concrete takes the compression, the steel takes the tension, and we design based on appropriate elastic modulus. What about wood? Is wood homogeneous? Why not?
Fibers.
What's that?
Like, I feel like there's different ways that the grain goes that causes it to have
The
different
grain.
issues at certain points.
Exactly. So we have, this is a dimension number. And you see there are grains, and if I do elevations, basically this is what is it? Mineral material. This is a composite material. This is biomaterial. This is a living material, right? So you have grains, you have cells that are connected together with natural glue, which is lignin. So here we have minerals like aggregates glued together with cement, and here we have a homogeneous material. So that's the concept of homogeneous material, and we have a concept called, what is it? Isotropic. What does isotropic mean? From structures one, you know it, you've heard it. Isotropic means the material behavior is the same in every direction. So in a steel, if I pull it or push it at any point, that shows the same load deformation behavior. In concrete, if I push it, I get this, then it fails. If I pull it, it doesn't even have capacity. In wood, it depends in what direction I push it. If I have a column like this, the grains go this way. If I push it this way, it has certain capacity. If I push it this way, it's perpendicular to grains. And if I pull it in this way, it has different capacity. If I pull it, so it's orthotropic, different properties in different directions. That makes it complex in design. For steel, we can design it in any direction. For this, the capacity of tension, compression is different, shear is different. Forgot to connect the. Where's the? Okay. All right. Are we still good with recording? I think so. All right. So we have different materials. The behavior is different. Their reaction towards different loading is different. So with the design process for this material is different. Although when we have a structure, we put the environmental loads on it, we calculate internal forces, but different type of forces, when we compare it to the capacity of material, in different materials is different. In steel, different response. In concrete, compression is taken by concrete, tension by steel. In wood, it depends on what direction. If you have compressive force in column, we compare it to its compressive capacity. Shear depends if it's perpendicular to grain or parallel to the grain, different capacity. So the idea is that we analyze them as certain type of material with their properties, and then we want to design them, we take account of what type of material they are, very different. Mineral, man-made composite, biomaterial. Any questions? Good. Precast panelized, the same idea. This one is instead of beam and columns, we have modular systems. We can have panels that are like kit of parts that come together. Okay, some cool questions at the end of this. All right, let's go. What conditions affect construction type? Building height, building area, fire rating, occupancy. Wait. Oh, yes. You have a question? What was it? The answer. Okay. All of the above, because as we talked in based on IBC, you have all of these depend on what type of structure you want to design. You can't design it from any material. Depends on how high it goes. Depends on what occupancy it has, right? So they're all What structural material has the highest fire rating? Concrete. Concrete is sometimes used as insulation too. So it's not combustible. It's what happens to steel when fire happens? What happens? Huh? Say it. It melts. But before it happens, it's the problem with the steel is you have certain time before it fails, but it doesn't fail when it fully melts. So we talked about the stiffness and load deformation. This is the stiffness that we talked about. When we heat up a steel, the movement of these molecules or the steel grains increases, this shifts. So it becomes less stiff, less stiff. What does that mean? It means that as it heats up, it starts, the beams start sagging under the same load. They start sagging. So it fails because of significant deformations. So the stiffness of the steel gets reduced as the temperature goes up. But concrete doesn't have this problem. That's why sometimes they kind of create a concrete casing around columns, metal columns. What the structural material is most easily adapted on site with hand or power tools? What? Huh? Wood. Yeah, that's why it's easier to build this smaller projects with wood. And also it's forgiving in many different ways. Cutting, nailing, hammering. A concrete slab, okay. A concrete slab can easily be punctured for vertical openings without affecting this. What? A concrete slab can easily be punctured for vertical openings without affecting the system. Okay, true or false? Why? You were very false, false. Why? Uh-huh. That's true. What happens? So if I have a slab, let's imagine I made a mistake. I just created a full slab. Now I forgot to put the stairs in. Why can't I just like cut a chunk of that middle of the slab and like pass the stairs through? You're right. I want to know why.
Why, right?
Yeah. What happens if you cut the flat slab in the middle?
The concrete can't support that, like the system.
Yeah, that's it. You remember we had continuous mesh of rebar, and in the center you have a maximum bending, let's say. If I cut this, it doesn't have the continuity to take the load, and it will have what is called progressive collapse. So we can't just, it's very important not to cut concrete slabs. It's very technical thing to know. They do these kind of things, but they calculate how much basically they think about this as this length is cantilever at that point. If it still can cantilever, then that should be fine, which means that the top mesh of a steel rebar should be enough to take it as cantilever. Because when it's continuous, this part is well, lower part here is in tension, but when we create cantilever, the upper part here goes into tension. So it's very difficult thing to do, but if it works, you should handle.
The thickness of the slab is calculated as well beforehand, based on where the openings are. Does that mean the thickness of the slab is affected, or would it be just over design?
If we
Like,
For-
if you're like, cantilever, it's fine,
uh-huh.
but what if the thickness of the slab is calculated properly?
That's it. A lot of times that doesn't work. You're right, because the thickness of the slab basically defines the arm of the tensile force from the reinforcement and compressive force of the concrete. And if it's designed for continuous single span, it's way smaller. When you want to design it for cantilever, it requires further, and that's why you can't. And most of the times you can't, and it's hard to reinforce this way. There are ways. Some of the ways are they use carbon fiber. These are the strips that they put on the tension side, but really difficult technical thing. So you're right. We can't cut the staircase in the central slab. A flat plate system has more costly formwork than a waffle slab. True or false? A flat plate compared to waffle. Yeah, I know. That's a trick question.
I thought you said the waffle slab is more expensive. I was like, yes, that's true.
This is how we get you in your test, right away. Cast in place concrete system have spans typically between. Okay. Cast in place concrete system have spans typically between 20 to 40. Not necessary, but this is not an accurate question, but cast in place concrete systems, depending on,
Right?
huh?
Not gonna be the test, right?
Hopefully not. This depends on what kind of system you're talking about. If it's beam, cast in place beam can be that, but if it's post tension, it can be higher. If it's a slab, it's higher. If it's post tension slab, it's higher. So it depends. It can be if it's simple concrete beam, but it can be way between 20 to, I don't know, depending on loading, maybe 100. So it's not, we should specify specifically what type. Precast concrete systems require crane and typically are cost effective for small scale projects. Okay. Who wants to answer this? Why are they not cost effective? Well, your answer was yes or no.
I got it. Honestly.
You go with your gut now.
Yeah,
Okay.
that's just my gut. Well, because they're not good for small projects. You said that 10 minutes ago.
They're not good for small projects, but also precast concrete is usually required.
What's that?
Some precast concrete systems typically require cranes to give somebody a large piece of wood.
They do. Yeah, they do.
So I'd say it's true.
Oh, okay. Oh, you think this is a two-part?
And
All of the questions are confusing. Okay.
yes.
But your test's gonna be really hard. All right. You're good. Yeah, as long as you fully understand this. This is great. Okay. Any questions? Let's take a short break. I'll come back in 10 minutes. Yeah, thank you. Come back in 10 minutes. So 7:20, 25, 7:25.
Hi. And then I can be possible because I didn't say the.
We're sorry.
Hey.
So I transferred, so like I said, in Canada, I didn't, no, I didn't do structures in one of them.
Okay.
Because they got transferred, but that was like 5 years ago. So I was just wondering when we study and stuff, do you give like, well, I don't want to say instructions, but kind of like explain how the process happens or supposed to, like, I already have a background. But is it more of like, where it's like, you should already know exactly what to do in steps and then we're just supposed to do the problem and solve it.
Okay. First of all, don't worry. That's okay. You have a background in architecture?
Yeah, so I did structural technology.
Okay.
And then I transferred to finish my master's here.
Okay.
So I didn't do structures 1 and 2, but they got transferred anyways. They gave me a transfer. So this is the only structures class that I have.
So you never took any structures classes?
I did take structure classes,
Uh-huh.
but I just don't know how the structure classes are here.
Oh, okay.
So I don't know if it's the same thing.
Yeah, don't worry, it's the same thing,
Okay.
or more or less. There are different systems based on how much they cover in each one.
Okay.
And there are non-technical, more design-oriented that they have different, a little bit different, but the bases are all covered.
Okay.
So you're good in
Okay.
terms of structures. And if you transferred, that have been acceptable. And for the type of projects we have, you should be good with following the class, also following the homeworks.
Mhm.
So you should be fine.
Okay.
Do not worry, that's all you need. You have all the instructions. And if you do good on the homeworks,
Mhm.
you will do good on the test. So
Okay.
just follow up with that, come to your TA and me for any questions. But there's nothing to worry.
Okay.
The only reason I asked that was that there's a prerequisite.
Yeah.
If the students didn't take it, they
Then they
should
can't.
know that, yeah,
Okay.
there was more administrative problems,
Okay.
but you're good.
Okay.
Yeah.
Thank you so much. I
Of
appreciate
course,
it.
yeah.
Down here.
Now that I've walked,
It's so hot.
you guys, I keep figuring out about like my eating. Like, when am I gonna eat?
No, I'm literally gonna start packing food.
Yeah, I guess I just.
Eat like this, you know.
Ian, you're not even on campus anymore, right? Go ahead. You're.
So listen.
What? I thought you guys still got an apartment for like now.
We're not allowed to live on campus.
Wait, what?
We're not allowed to live on campus.
Why? Oh,
That's weird. We don't want to sign.
well. Yeah. It's pretty warm.
Good night.
I'm so glad we don't have any soup.
Yeah. Oh.
That's really.
Guys, it's 84 fucking degrees in here.
There's no way, it's so hot.
Any way to turn it down?
I'm trying,
84?
I swear, it doesn't even let you change it.
This should be I can't. Mine's best.
I'm gonna take a picture of that. And tag LTU.
I said I wasn't gonna.
Oh my God. Where did the teacher go?
You didn't want to be.
How do you guys feel about him?
I think time moving on go faster than
Oh, yeah.
He doesn't talk with million miles an hour right now.
And he does things on the board, I love that. Ooh.
Really? Lexi.
That's like 84 degrees.
Lindsay, what is Lexi on with?
She's always like this. He hit her with the join a group of 30. You know.
Dude, that was funny. Sometimes too long.
Yeah. Our studio. When I get it. And then like, when I get full, it's like they wait like 2 weeks, turn on that. I don't know what it is. I don't know what it is.
I'm Armenian, Iraqi.
Oh, yeah.
Yes, we are. I know. Okay. My shirt inside of the. She's too right there.
Sorry. There you go.
Oh,
Nobody's ever talked about it. You might turn it on. There's a lot of great stuff on this. You know, But I found it.
Oh, yeah.
Yeah.
Yeah, thanks. You kept it open? Perfect. Yeah, sorry about the yeah, temperature in here. Just we're gonna talk about this. Hopefully we can get the AC going.
It should be cooling down here.
How's your 9 to 9? I'm still awake.
Can we look at a fan? I don't know. I'll check if you want. It's early spot. No, 88 degrees for a caution as well. Yeah. No, we should get a better. And we.
Kitchenette, not bedroom, kitchenette.
They'll make so much money on us. They already do. How about Pastor didn't give you money this semester?
All right. Yeah, we can hold up around 1 hour and 15 minutes more, and hopefully we get this resolved for next session, hopefully. We are in this together. No, I thought I was actually happy that this is a nice room for presentations. I didn't expect this. Yeah. Is it always like this? Oh, okay.
Oh, it's actually normally cold, isn't it?
So it's just a matter of them getting the AC going. Is that?
Well, I mean, that was sticking outside of the wall when I looked at it. So I think something is wrong. It was hanging, I just put it back. And I read. No, it'll probably fall off if you touch it.
Everything that happened in that building, it was just so terrible. Also, it seemed like the AC wasn't running very well in the first floor.
No, level B is level 1 is so much cooler. Can you imagine being on the 4th floor like freshman year though?
Yeah, I was there. They literally had like 11 every single time. It's not, they just kind of-
Freshman year, 4th floor was sick.
Yeah.
Those are all the light control.
Yeah, sorry about this, but we should be fine for next session. I'll make sure they take care of it.
Thank you.
Yeah, sorry about this. All right. Let's do the second lecture. So much excitement. This helps with the let's distract from the heat by some. What is that? Yes, this is still, so this is the third part. We talked about wood and concrete. This is still, yeah, it's still kind of a general information. Yeah, we've started. Focus. All right. So again, the same overview on structural systems. We talked about wood, we talked about concrete. Now we're gonna talk about steel. It really helps with let's distract ourselves by some over exaggerated excitement. Yes. Steel framing systems for gravity loading. So general information, system design factors, weight of the structure is relatively light. Relatively means compared to concrete. And lighter structures in general mean lighter. So this is very probably self-explanatory, but important to understand. One of the ways you can think about sustainable design, one of the ways is to think about more lighter structural system. And this lighter structural system can come from the type of the choice of material you have. Are you using concrete, or are you using steel, or are you using wood, right? But again, next step is whatever you chose, are you designing it in an optimal way that the structural elements are smaller or better distributed or whatever it is? Reducing material, reducing weight means that the structure has to take lesser load, which means it's kind of a dynamo. It just gets a smaller members on the lower levels, a smaller foundations, which has a lot of concrete and causes significant carbon footprint and tons of excavation depths that you have to work. So lighter materials, more optimized systems, lighter foundations. So you're reducing a lot of material by thinking in these terms, right? But the choice of material matters too. Concrete is heavy, but if you want to go higher, you probably need concrete. Steel lighter, but if you're going to higher, you need thicker steel plates or built-up sections. All of these play into bigger foundations, more excavation, more concrete, bigger footprint. So thinking about structures in terms of weight is a good starting point, but it's not the end point. Think about the good material you use, optimize the structural system, optimize the construction system, whether you can use prefabricated members, whether you can use more optimal elements, construction, assembly, fabrication, whether you can design for disassembly and use part of the demolition waste. Things around this. So throughout the life cycle of the building, you can think about efficiencies early on in your design, from material to structure, to fabrication, to construction and demolition. So steel is lighter than concrete, means lighter structural system overall in general. Steel can be prefabricated, can also be done on site. The connections, you have different types of connections, whether it's fixed, which means it carries bending from beam to columns, or it's shear connection, which just takes shear. It can be bolted, it can be welded, it can be prefabricated, it can be welded on site. Versatile material. Depending on what type of construction you do, you might need skilled workers, skilled welders. Depending on the complications of the geometry, you may require, so some of the, let's say, framing systems, a lot of the connections are well-defined and easy to create. But sometimes, let's say you have a space frame, I'm going to talk about this. These are linear elements, so simple elements, but the nodes that they come together is a complex node. So you might have to cast these or paint these. Nowadays you can have 3D printed metal. So the complications here from the elements goes to the nodes. Complicated nodes, different unique nodes in the structure means different unique work, costly, more cost added to the project, more time of construction. So a lot of things at the same time you think about. You don't think about the structural capacity optimization as a structural optimal geometry. You think about it in terms of how it's assembled, how it's fabricated, how it's put together, and what happens after demolition. Economy and cost issues in design of low to medium burst steel. As we talked, we have different grades of steel, A36 and A50, and that depends on the carbon content when they manufacture the steel type, right? But so in terms of the pricing on that is different. So high capacity steel, we have mild steel in A36, and they have ultra high capacity steel, which is used in cables and things like that. And this is a structural steel. A36. One thing to consider is that while A360 has lower capacity, and that's the yielding capacity we talked about, however, this is more ductile. Talk about ductility. This is more brittle, which means when we test them, this one goes, this is A360, and this is A360. So it fails, it takes less energy before fail, but it takes higher load. Energy is the amount on release this. And that matters when you work with seismic, with airstrike. So higher capacity, but less ductile. Ductile means that it can expand before it fails. Any questions? Okay, okay. These are more general in terms of the material, and we get to more structural aspect. Economy and cost, moment rigid connections are more costly than shear connection. We talked about moment. Okay, so this is a shear connection. Let's say we have a column, double section, and there's a beam, again, double section, and this is white flange. And then they have bolts, and then there's an angle, and it just transfers shear. But if I have this beam, and it comes to column, and I develop the plane, it transfers bending moment. So this one means that when I want to model that, it's this, let's say, it's simple beam. This one it's not fully fixed, but it has fixed. So this one takes more load because the bending moments is like this, and this one less load because bending moment, maximum bending moment is bigger than this one. However, this is more expensive because we have to develop both top flange and bottom flange, right? The transferring moment is helpful because it reduces the maximum moment. So we can actually more optimal design. And also in earthquake, this one takes moment, which means it can take part of the lateral stability of the building. But this one doesn't, it's laterally, it's not stable. So we have to have bracing for this one, right? So again, complications. We have bracing, easier connection type, so less skilled worker, faster construction, easier construction, require bracing, less openness in facade. You're going to cover your windows, right? More openness in the facade, more complicated connections, more skilled workers, more expensive. But we can design it more optimally. Depending on the budget you have, you can decide, or needs. If the program needs, let's say, a very open facade, you can't have bracing, you'll use moment frame connections. Or you can pair both of these with shear walls. Some of the spans will be covered with shear walls. Any questions? Okay, so it's very general, but we talk about these things in more details. Okay, rigid frame members use minimum number of rigid connections, avoid the use of built-up sections. What is a built-up section? Yeah. Sort of, yes. What are the modifications? Yeah. So that's called reinforcing the section, but we have rolled sections, which means in a factory, they roll these bars repeatedly through rollers, and they create I shape, right? This is rolled section. These are W section and Y flanges, right? Built-up plate is that you have basically girders, usually for higher load-bearing capacity, when they need bigger depths of the beam, they use plates. So you have one plate, you weld it here, you weld this here, or you create boxes like this. These are called built. This is all welded. These are built up. This is rolled. Built up, which means that this is limited height. There are limited heights of these in their tables. You can look at all the properties of section, but the height of the beam, which is the capacity it has, based on the depths, is limited. But you can build whatever depths you want with built-up sections, usually in girders and big spans or in bridges. You use built-up sections. However, as you can imagine, there's fabrication costs and transportation issues and uniqueness in construction. All that comes as you can source it from the manufacturer. Any questions? Okay. So here what is saying that is kind of, again, a general recommendation on when you're working with steel members, are you going to use simple connections or rigid connections? Rigid connections are more expensive. However, as I said, it brings in some efficiency compared to simple connections. And then depending on how you design, you can play around with number of them and strategic location of them in the framing system to figure out the best configuration for that beam connections to the columns and beams to beams. This is an example. A similar span and a floor plan and different types of integration of whether the columns are rigid to beams, and it kind of shows the pound per square foot use of steel and shows like 4 different options. The one on top right is most expensive. Which one is least expensive? The first one is on the left top part is least expensive. So the combination matters and a lot of other factors, not just the structural efficiency. Minimize number of elements and rigid connections. And again, this is all generalized, but it all depends on what kind of loading you have. Is it dead loading, live loading, whether there's a point loading from mechanical systems at a certain location. So it can get more complicated than this, but as a general rule, figure out the most straightforward framing system that kind of unifies the use of elements, makes the construction easier. However, you might go through the route of optimizing the system, minimizing the number of elements, increasing the depth of elements if the required height in your structure lets you do it. So you play around with some of these options. There are different factors in play to figure out what is the more efficient in a larger meaning option is. This is again one of these nice tables for kind of the rules of thumb, a span to depth ratio for different steel systems, corrugated steel decking. We're going to talk about this light gauge joist, open web steel joist, W sections, built up steel plate girders, steel trusses, 3D trusses, arches, ribbed domes, cable structures, the space frames. Here is again another table for one-way, two-way system, different structural systems, beams, trusses, form active and vector active systems, and then the span to depth ratio. As the span goes up, of course, the depth increases. But what type of structural system can accommodate that span in general? And what is the common uses of these I'm going to talk about? Any questions? I'm going to talk about each of these more. Okay. W sections and composite steel concrete. So this is a very common way of building, and it kind of adds some optimality in design and use of the steel. And that's when so you can have your steel beams. You can have your steel beams and put your flat plate on top of it, or you can put studs, shear connectors. When you put the shear connectors, these are shear connectors, the studs are welded on top of your beams, along the beam, which is the top of the uniform elevation, there here, right? And pour concrete. When concrete cures, this part of concrete works as a composite with your steel, which means that, this is the I section. Which means that again, in the same way, concrete takes the compression and this whole thing takes the tension. So increases, they work together instead of each of them working separately. So this increases the load bearing capacity of the beam. So you can use actually a smaller beam compared to non-composite action. So that's when you have shear studs on top of the beams, and then you pour concrete onto it with corrugated steel. We have steel truss joists and plate girders. So truss, open web joists, where have you seen open web joists? Yeah. Yeah. Costco. That's a very common thing for lightweight roofs. Is a roof system usually. And this can be as deep as you need it to be, depending on the fabricator. But this is lightweight and it's kind of optimized. It moves away angles with the steel wires in between, that as they move it, they increase the moment arm in the system. Very lightweight, prefabricated, easy to install and create the connections to the girders. And the plate girders, again, built-up systems. Sometimes you have built-up sections, sometimes you have plate girders. We have what we call veer and wheel trusses. That's also I have this system that all of these are welded, and it's a truss, but it works as a beam. There is bending in all the elements. Any questions? Okay. Column supported frames, basically post and beam, steel beams connected to steel columns. All right. This is a good example of using a steel framing in as part of which is part of the design language in a way. How is the steel choice of a steel in the system is appropriate? How is the steel contributing to design in this? Yes. Why is it interesting? There's certain simplicity in it. And also it shows the structure very lightweight in a way. there's an interesting way they use bracing in a facade, which usually is frowned upon, but they figured out a way to use it. It kind of integrates really well. What are they doing with the bracing that actually is taking away that blocking nature of bracing in facade? They're doing something interesting here. The bracing is happening, the X bracing is not happening in the height of each floor. It's a chevron bracing that spans in 2 floors. Right? Imagine if they use this like this, how it felt like. And now they did this. This is a different type of bracing. It's more flexible, but it also kind of changes the way the heaviness of the structure is reduced. Also, they made it look thinner with elevation, with extended elevation of the floors. Like this, the simplicity is great. And it became kind of a high-tech steel glass facade. Creative work. Okay, beam and column transfer beams. This is an interesting concept. What is a transfer beam? Does anybody know about this concept? What is it? Uh-huh. Exactly. Why do we break the vertical continuity? Exactly. So there's a lot of times in a mid-rise or high-rise buildings, if there are traditional framing system, what happens in the lower levels when you have commercial spaces, you require bigger spans. But the structure itself could not be designed with those big spans. So you have these columns, it is optimal design, but you realize that this is not appropriate for the commercial spaces. So when you reduce this to this, or let's say you have 4 of them, we're going to reduce the middle one. What you do is that you have this beam, huge beam here, that takes the load, which is accumulated load from here, transfer it to these columns, and transfer it to the foundation. This idea is that the load paths have been broken, so it's not optimal structurally, it's not optimal, but responding to programmatic needs on the lower levels. And this can happen on different levels, and they use these huge trusses sometimes. They call them outriggers in the high-rise buildings. But the idea is that you break the load paths with different types of systems to transfer the load to the closest or closely existing columns down the way to foundation. This is a common way of accommodating for programmatic needs, as you mentioned. And this can happen different ways. You can have a deep beam, you can have a deep truss system, outriggers, or you can have suspended systems that the columns, instead of columns being in compression, columns are all hanging from the huge truss from above. So all these columns are in tension. There is no, and there is a load bearing wall all the way. So hanging all these plates. Or using trusses, as you can see. Any questions? Okay. Diagrid frames. So diagrids are basically, imagine a brace system that happens on the facade of a building, which is not just the facade, it's load bearing, it's adding to the stability of system, it adds to vertical load bearing. So it's taking the load, bringing it down to foundation, but also it takes the lateral load, which is the wind or seismic loading that happens in a structure. It usually is used on, well, this is a unique geometry, this is a sphere, but a lot of freeform geometries, a lot of freeform facades, they have diagrid systems whether as a main or primary load bearing or secondary or tertiary load bearing system. Do we have any diagrams around? I don't know. Do we? Is there a diagram structure on campus? I don't know. No. There's one, huh? What is it? Okay. Um, bridge type building. So again, this idea of, and it happens in designs like this, where you have blocks of structure spanning or cantilevering. We use this type of, one of the ways to optimally design this is to create these huge trusses on the periphery of the structure. You have a box, imagine, and then you have these huge trusses that then you have this longest span concrete hollow core of roof system. So it spans without column, but then these trusses are both vertical load bearing as they span out, and are also lateral load bearing. So it's an optimal way of thinking about it. And if you can integrate it into the structure, it becomes part of the design. And this was one of the ideas on the big design for Claremont McKenna College. There were 3 boxes, there's 6 boxes rotating on each other, and there were these huge trusses on 2 sides of each box. And the best system to do that is steel, obviously. Here's a space frame. So again, space frames are particularly interesting as they are these lightweight structural systems that span significantly large spans, and they're built up of simple elements, tabular elements. Here. And so you can design them basically with highly optimal limited variation in diameter. So usually where the location of supports are, we need bigger sections, but you can design it in a way that maybe 3 or 4 types of tubes are used throughout the structure with significantly large spans. Again, if you design it with the modularity and repetition, all of those pieces can be prefabricated and craned in and connected, and it can be fast. But if you have a free-form geometry, then there will be significant variation in nodes. And these nodes are still casted nodes, and that can be significantly expensive. There are different ways they approach when there's complexity of connections. If they have free form, they use techniques called clustering, which means they analyze the system, they figure out where the forces are actually going, and they cluster pieces of the structure based on the forces they have, and they use similar diameters for those. So they are not structurally optimized, but fabrication-wise optimized and construction-way optimized. So we have these clusters that have all the same members and connection types. So it deforms a geometry, which is called rationalize the geometry in a way. So the geometry will not, I'm exaggerating, of course, but the geometry will deviate from the actual smooth free form or whatever they have, but they're structurally and fabrication-wise optimized. And a lot of artificial intelligence methods are helping with this, called clustering methods. Any question about this? These are some examples of using space frames. Probably one of the first uses was airplane hangars, as you need huge, still they use this, right? It's huge space frames that create open spaces for planes to park in. Portal frames, steel prefabricated portal frames. Where have you seen portal frames? I've seen them a lot. Industrial, what else?
Pole barn.
Yeah, what else? Gymnasiums. Churches, churches, so depending on, huh? What? Newer. Yeah, modern churches, yes. Older ones, usually heavy timber or masonry, right? What's that?
I did portal frame mass timber for my ID3 project.
Beautiful. Yeah. So there are exactly a lot of industrial gymnasiums, still a lot of industrial buildings use this system, and it can be prefabricated, it can be optimized significantly in terms of the structural performance and also transportation. It can be welded, it can be bolted, depending on the need and size of the spans, but it can be transported or not. The other counterpart is, of course, is still trusses, one of the oldest methods of spanning larger. Again, barns, gymnasiums, more modern designs with that too. But the concept is the same. Here's a good example. What is this? This is a looks like an congregation space.
What's your favorite material?
My favorite material? So I like biomaterials. A lot of my research goes to biomaterials. So if in the structural materials, I like mass timber most, but how we use biomaterials.
What's the construction for mass timber?
Choice of construction? Well, prefab, volumetric, and the most simple post and beam, but detailed well. Those are my favorite. Yeah. It's an interesting material, and codes are becoming more and more open to these. So more mid-rise to high-rise is buildable now.
Have you had that work on any of those?
So I worked with the proposal for, I showed you a picture for mass timber rooftop.
Yeah.
But that was an addition to existing buildings. So it was, and the choice there was not, I personally like this better, which is adaptive reuse, extension. But the idea was this was added to existing building. The main design driver was minimizing material use and location of columns to not to need to retrofit foundations. This is affordable housing. There is no budget for it. You want to look into ways that you can enhance them without much budget.
What was the existing material?
It was concrete. It was built in one was 1945, one was 1965, I guess. So there are old buildings which are kind of falling apart. It's still structurally sound, but because of the maintenance in the roof, they have bad conditions. And this was a renovation effort. So there are two aspects to it. No, multiple aspects, but two main. One was rooftop and the other one was balconies. And then in the study, mass timber made sense. Yeah, exciting opportunities. It's expanding. It's been around like way before in Europe, and they have moved forward with that. They're like 15 years, 10, 15 years behind them, but it's taken up and it's picking up in US too. So that's my favorite structural material, but still hasn't find its place, mostly because of economic reasons. It has a higher upfront cost, and also the scheduling is different. When you design these, they're prefabricated, so you have to schedule them way ahead, and there are issues with that. Logistics are more complicated, but mostly the owners do not build because lack of technical expertise and also upfront costs. You can save some costs by creating faster delivery, but this is hard. As long as you can convince your client. But yeah. Any questions about steel framing? This is a exploded axon of that system. The other specialty structural system is membrane structures, which are these textile structures which they find their stability through combination with other materials, steel systems, textile on top, or mostly steel and cable systems. You guys know this structure in Detroit? Transit center?
Airport.
The airport? Which airport? DCW?
The McNamara terminal. He said it's important, I don't know, it looks like TW.
But no, the same system, huh?
Yeah, and the McNamara terminal on TW for Delta.
Oh, it's by the entrance, huh? The entrance of the
Yeah,
right.
right.
Yeah, you're right. You're right. But the concept is the same. So this is a lightweight system. The stability comes from, for example, in this system, you see the columns, they triangulated, they stabilize the system. The trusses take the loads from edges, the cables stabilize the trusses and the columns, and the shape of the membrane is basically created by boundary condition and stability of overall structure. So the difference in membrane structures is that they are not designed by themselves. The form is not designed by itself. The form is informed by boundary conditions and loading situation. So the trusses and the columns and the cables, columns are in compression, trusses are in bending at the edges, and the geometry of this, whatever that is created by the boundary conditions, which means the steel elements, location of these supports, and the forces. These are pre-tensioned, so they take this minimal surface shape. This is different than, for example, you create preform concrete. Right? You create a formwork and build this. This form is you design it and build it, but this is kind of informed by the location and the type of loading and the boundary conditions. The good thing about these is highly lightweight, less use of material for cladding, can span large with basically not much material. And although the textile is PTFE or Teflon and different types of that, but the material itself is not environmentally friendly, but since you use way much less material in general, it is one of the sustainable approaches to design. But it's a specialty design. The fabrication techniques for cutting patterns in the membrane is a specialty. And so it has a lot of technicality, stability of these. We talked a little bit about this. We have bulk active, vector active, form active. This is kind of what I just talked about. What I talked about is form active, which means the geometry is a result of overall design, boundary condition, forces. Bulk active is basically this, that you optimize the geometry based on forces. Vector active is basically space frames and trusses that the system is, all of the elements are just in tension or compression. There is no bending. So you transfer loads by tension and compression. This is called sometimes catenary, sometimes funicular shapes, but in terms of trusses, they are tension compression elements. Here is an example of a beam, optimized beam and a truss system. Optimized truss, which has bigger depths in the location of maximum moment. Funicular cable. What is funicular? What is a funicular shape? You know this. Or funicular shapes are the geometries for cables, means the shape that a catenary curve. If I have a cable and supported at 2 points, it takes a shape because of its weight. This means cable can't take any compression or bending, right? So it means all of the pieces are in tension. So that geometry under its own self-weight causes only tension in the material. If I freeze this and rotate it under its own self-weight, I have a dome which only is in compression. There is no bending in this. The geometry of this means that it's optimal design, because let's say masonry or concrete is weak in tension. If I design it this way, so inverted cable, under its own self-weight, it only carries forces in compression, which is the best way the material can work with. So optimal geometry is this. This is called funicular shapes. So catenary cave of a arch, a cable, when I invert it, it becomes the optimal compression only funicular arch or dome. This is basically what it is. So you can design, this is kind of a structural optimization technique. And if you've seen works of Gaudi, he was using what is called hanging chain methods to design these cathedrals. Basically have a network of wires and hang sandbags from it, inverted, that informs the funicular shape in 3 dimensions. There were no computers, of course. So this was a physical way. And when you invert it, if you build it that way, it's all in compression. A good way of doing masonry structures and optimal compression only domes and geometries. So funicular forms, again, form active funicular arches. Any questions? Okay. Again, optimization in terms of form active and vector active. Normal column, solid column, takes the compression load. If you want to optimize it, there is a particular behavior in columns when elements are in compression that we have to pay attention to. What is that? What are the failure mechanism of a column? Buckling. Buckling is when so if I put that same column in tension, it fails when it disconnects the material disconnects. But if I put the same element in compression, and if it has a small cross section, it fails not because it crushes, it fails way before that by buckling, sudden change or sudden deformation in its shape, it buckles. And this is the behavior when material gets into compression and it has thin cross section, a smaller cross section. So in order to optimize that, if we increase the depths of the column in the middle, we can just move the material away from center of it, use the same amount of material, you can significantly increase the load bearing capacity of that material. So based on structural behavior, you optimize it by, instead of having a solid system, move the material away in the center. So it becomes the same material, the same amount, the same height, still can take maybe twice as low. The other way is to use truss systems and create, basically you're distributing material in a very linear, discrete system. Or the last one, which is form, called form active. These are like general terms, but it's instead of increasing the material and distributing it away from it, I am going to support my column at the center by creating this form active geometry. So instead of actually using where I can use veilless material, if I have this column that is under and it buckles. If I add a latch here and two cables, I have significantly increased the buckling capacity. Is still with the same element size, these take tension and doesn't let it buckle. So it goes down until whether the cables fail or this crushes. So I increase the load bearing capacity in compression in a form active way. These are interesting ways to think about creating interesting forms which has a structural logic behind it. Again, buckling happens in all materials. This is increasing the thickness of a column in the center is an optimal way instead of just using a bigger section all through. But again, you can see that they carved the material here. So it has more visual interest than material optimality. The same optimization of trusses, whether in 2 dimensions or 3 dimensions, based on the load-bearing mechanism and depths. Integration of systems, we kind of touched on this a little bit. We have, so in general terms, for the building, you have foundation, superstructure, exterior envelope, interior partitions, which are not structural, mechanical systems, furnishing materials, and integration of systems relates to different ways that different building systems are integrated. And it depends on the type of structural system you use and the type of collaboration you have with the different trades in your project. But basically, it can be remote, meshed, and unified. If you integrate your system in your structural, integrate different trades in your structural system, what is the issue with that? What is the upside or downside with that? If you integrate all your systems in your structure, what does that mean? I give you a couple of options. The first one is here. The systems are not integrated. So the slab, the HVAC, electrical, they have a drop ceiling and they're all hidden and everything is basically available. The second one on top is that we have a truss system, so it has openings that I can run the mechanical systems and electrical system through. And the third one is prefab concrete system that has all the system integrated. What's the difference? What is the good side about integrating anything? ID1, ID2, ID3. What is the use of that? Save a space. Reduce the depths of your roof system, the floor system. The integration, you can think about prefabrication and delivery. It can have higher quality systems if all trades work on that together. What is the downside? Maintenance, accessibility, exactly. So it makes it difficult in terms of maintenance, but also there's one bigger challenge. When you think about when your project requires changes in program in future, you don't have accessibility. It's not flexible in terms of programming. So it all depends on what kind of project you're working on. A lot of times there are systems that you can mesh, you can use the mesh system integration, which means using systems that have accessibility that mechanicals can run through, electricals can run through, but there are also, there's also accessibility. There's also maintenance availability. But sometimes if it's, when you think about volumetric prefab construction. In those terms, you basically are integrating everything into your wall systems, roof system, and it comes in as plug and play. You have the walls, you have the roofs, just come together, right? There are new ways of doing this. It complicates the process, but if you work with all the trades and you figure out the details and also how these different trades work on site, you can manage to do that. But it should be based on the type of program you're working with. This is a good example. Oh, the nice part. Are you ready? What's the energy level in the Are we dying of heat? You hold up really well, by the way. I didn't expect you guys to not pass out. Because I am half awake. Huh?
Great, parents for our last semester.
Fresh air.
Yeah.
I'm glad I am. You don't know this is the first class. How do you know it happens? You haven't so far. So far. Okay, okay. We never know.
Yeah, those trick questions, man, on those, if we sit on.
Ah. Those keep coming, by the way. Yeah, so let's wait a little bit longer. Good. So okay, let's do this. Ready? Which system can span the largest dimensions, wood, concrete, or steel?
Wait, I heard all three.
Yeah, this is good. This is good. Why? So which one is it? Is it between the steel and concrete? Is that it? What you're saying? It has to be steel. Okay.
What if steel is in the concrete?
You even if there is no trick question, you make it complicated. All right, this is true that it is a steel, but also it can depend on the type of construction. Like if it's dome, it can be concrete domes can span large spans, but we have steel domes, space frame. So I go with steel. Concrete waffle slab system easily be disassembled when compared to a steel column beam frame. No, because it's just poured in place, poured together. There is no disassembly, right? What material is generally considered most sustainable, wood, concrete, or steel? Why? Why wood is more sustainable? Huh? Reusable? Grows out of the earth? So grows back. Okay, replenishable resource. Okay, what was it?
Like, wouldn't you sit on different projects?
That's true. That's true. Okay. Okay. Say it again. Yes, there is one more reason. Who knows this one? This is very particular to biomaterials. And I mean, not all of them. Wood in particular. Huh? Yes. Yes. What does that mean?
That its production process enough carbon, then it would actually release. So like as it grows, the tree takes in carbon,
Yes.
that it's a net negative on the carbon footprint.
Yes. So the difference in this is why wood is amazing, is that part of the reason that's my favorite is it's a biomaterial. It grows. The interesting thing is we see trees. Trees are mostly carbon. So they just get CO2 and water, and it creates wood fibers. So they capture CO2, and this is what causes the big issues with productions of other materials is that they produce CO2 and release into the atmosphere. They capture CO2. So when they are growing, they're actually capturing CO2. So if you cut them and use them in a building, you're basically keeping this CO2, they call them CO2 sink. So it becomes extend the life of this CO2 from the earth into the building. So by cutting the trees, they grow back and they continue capturing CO2. And when the trees are younger, they capture more CO2. So as they grow, that process slows down. So we cut them, we use them, they're actually sinking, keeping CO2 in the structures and do not release it to the atmosphere. So many reasons there why wood is sustainable. And one unique way, it's a carbon sink. Okay, very. Which system is often prefabricated? Portal frame, composite steel concrete, steel truss. Steel truss is prefabricated. Portal frame can be prefabricated too. Yeah, so those two. Composite steel concrete is cast in place. So, which material has the lowest fire rate? What's that? Okay, you were just now answer before I finish the question. Okay. No, you see. Name 2 reasons why a remote system integration strategy makes sense for short duration occupancy condition. Okay, remote means not integrated. 2 reasons why remote system integration makes sense for short duration occupancy conditions. Say it. We can change it. What is it? That's it.
It says two reasons. What's the second reason?
Oh, I see. There are 2 reasons. Okay, one is probably coordination with different trades. So you don't have to really coordinate much. They do their own thing. Name 2 reasons why a steel concrete composite system would be used for high-rise office construction. Yeah, lightweight, more optimal, partially prefab, I guess. Any other reason? Fire resistance, yeah. Still,
Larger.
yeah, if you use combination, you're basically reducing concrete, which makes it more lightweight, a smaller foundation. Okay. Was that what you meant? Okay. Okay. The steel systems often have good seismic performance because of vertical continuity. The steel systems often have good seismic is like earthquake performance because of vertical continuity. I know, it's a confused. So steel systems often have good seismic performance because of they have vertical continuity, means rigid connectivity over on across the frame. Different. It's a bad question. But the answer. Huh? Yes, these are Professor Forrest questions. We share exams. They're not done yet. Yeah. You're skeptical. It's gonna be confusing. It's gonna be confusing. No, that's you'll be
Now I'm
fine.
not skeptical, I'm certain.
Okay. Should I answer that? That's yes, because steel systems, you create continuity, which means rigidity and load pass is continuous across all floors from roof to foundation. And the general rule for seismic design is simple load pass. You take the load, bring it down. Any breakage of load causes problems in lateral load. Thank you so much. Your homework is due next week. Our next session is after Labor Day.
On Monday.
Yes. Yes. Please do your homeworks on time, and
Yeah.
you don't have to, yeah, before Labor Day. That's it. Yes. Submit that. I'm not gonna be too strict about that one, but do that, because if you keep not doing it, it's gonna be hard to catch up. Hold on, your quiz. Everybody should be paired and chosen the project right now. Okay? You're good too. Any other questions? All right. Absolutely. Thank you. I'm gonna take care of this, hopefully, so you don't have to suffer.
So cool last week. Thank you for the invitation. Expecting it.
I know I didn't expect this at all. Yeah.